By this point, you should have a note sheet out front that says Introduction to Logarithms. Looks like what's on the screen here. Make sure it says notes in the corner and not homework. And if you can also grab your graphing calculators, if you don't already have it out, today's kind of a big calculator day, or at least a little bit of a calculator day, so make sure you have that. So take that out as well. Give you a couple of seconds to do that. And just make sure you're following along and filling in the notes like usual. All right, so introduction to logarithms. Logarithms are a new type of function that you haven't seen before, and we're doing them right after the exponentials because they're pretty closely related. Okay, so what is a logarithm? Well, a logarithm is a function that undoes an exponential function. And if it undoes another function, it's another word for that is saying that it is the inverse of an exponential function. Just like multiplication and division are kind of inverse operations. Another thing to think about when you have something like x squared equals y. When you're squaring a number x, what undoes a square? Square root. So you would take the square root of both sides, and you get that x is equal to the square root of y. And that's something that everyone's very used to, and none of you really question why this square root and square just magically go away in this step here. You just know that it does. That's the same type of thing with logs, and that's what you want to think of with logs. Logs undo exponential functions, so they get rid of the base. You know, when I've got y equals b to the x, eventually when you see me take a log of both sides, it's going to get rid of that base and leave me with just x. It's just like the square root got rid of the exponent of 2. Okay, so let's look at some logs graphically here. It says consider the exponential function f of x equals 2 to the x. Use the calculator to sketch a graph of f of x. All right, so if you want, you know we've done this a lot before, you can go to y equals in your calculator. You can type in 2 raised to the x. And as long as your table is set on ask instead of auto, independent open on ask there, I can go to second graph to get to the table. And let's just look at -2, -1, 0, 1, and 2. Okay, so there's my values, 0.25, 0.5, 1, 2, and 4. And that kind of just confirms what we already know. If I make a table of values over here, I've got x and y. I'm just picking -2, -1, 0, 1, and 2, so I have a good representation of points there. And I'm doing this without my calculator. I would usually start with a 0. 2 to the 0, you all know, is what? 1. And then 2 to the first is 2. And 2 squared is 4. And you know enough about negative exponents to say if 2 to the first is 2, 2 to the negative first would be 1/2. And if 2 squared is 4, 2 to the negative 2 would be 1/4. Remember, negative exponent just means to flip. All right, so let's plot that. So over here you've got -2, 1/4, so right about there. And then -2, 1/2, a little bit higher, 0, 1, 1, 2, 2, 4. Plotting that gives you f of x. So we've done a lot with exponentials. That should look very familiar to you. Remember, what else do exponential functions have that I usually graph? Horizontal asymptote. So there's a horizontal asymptote here at y equals 0. So go ahead and put that in. Okay, and then if we answer these questions down here, we just said horizontal asymptote is where? Y equals 0. Y-intercepts, we always know y-intercept is happening when x is 0. You know the y-intercept of every exponential parent function is always 0, 1. Okay, domain and interval notation. Well, it goes left forever, and it goes to the right forever, so we know domain of exponential functions are always -infinity to infinity. And range, what's the lowest this graph goes? Well, the lowest it goes is right here, down to 0. And what's the highest it goes? Highest it goes up forever, so it goes up to infinity. And like always, we got an asymptote at 0, so that's in parentheses as well. End behavior, you've seen this before too. As x goes to infinity, So here's my x values. As they're going to infinity out this way, what's happening to the y values? They're also going to infinity. Okay, how about as x goes to negative infinity? As x gets this way, what's happening to these y values? They're not going to negative infinity because they're not down here or anything like that. They are approaching the line y equals 0. Okay, nothing new. We've been doing that for weeks. Now, when you go down here, it says to sketch the graph of the inverse of f of x. Okay, well, when you see the word inverse, what's inverse mean? Hopefully, you're all screaming, switch x and y. Because inverse always means switch x and y. Got a little too many hands in there. All right, so if I make a table of values, and I'm even going to switch the color, so we'll do red now, so you know the difference. Here's x and y. This is for my inverse function. Take your original table of values from up here and just flip them. So we've got 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2. So now take those points and plot those on the same axes up here. So we're going to graph 1/4, -2, which should be right about there. 1/2, -1, 1, 0, 2, 1, 1, 2, 3, 4, 2. So connecting those points gives you this graph. All right, now to identify, actually, let me write this as f inverse. Remember that notation, so f to the negative first power, f inverse of x. Down here where it says to identify for f inverse of x, it talks about a vertical asymptote. Okay, well, think about it for a second. If the horizontal asymptote was y equals 0, when I switch x and y, what's going to happen to y equals 0? Well, it's going to become x equals 0. So we should put that in our inverse graph as well. Go back up to your graph over here and dot in x equals 0. So that's part of there's a vertical asymptote with the inverse of log, or inverse of exponentials. Okay, back down here, the x-intercept. Well, before we had a y-intercept of 0, 1. So when I switch x and y, now I have an x-intercept right there of 1, 0. Okay, let's look at the domain. When you go back up and look at that graph, the domain, what's the farthest left I go? Well, I never go any further left than x equals 0. And what's the farthest right I go? I go right forever. So I would say my domain is parentheses 0, because of that asymptote, to infinity. How about the range? Look at this red graph again. What's the lowest it goes? Negative infinity. What's the highest it goes? Even though it's growing slowly, it is still growing forever, so it does go negative infinity to infinity. And take a look real quick. Compare these two domains and ranges. What do you notice? We should be saying they switch. And that should make sense, because domain is like your x's, range is like your y's. And when you switch x and y, you're going to switch your domain and ranges. Okay, all stuff we've seen before. Last part here for end behavior. As x goes to infinity with this red graph, so as my x values get huge, what's happening to my y values? They're also getting huge, just getting huge at a slow pace. So as x goes to infinity, y goes to infinity. Okay, how about as x approaches 0? Well, as x approaches 0, my y values are getting lower and lower and lower. So as x approaches 0, my y's approach negative infinity. Okay, page 1 down. Hopefully you got all that filled in. Here we go on to the next page. And go. All right, same question, but now I'm asking what is the equation of the inverse of f of x equals 2 to the x? Okay, now here's where the new stuff comes in. You know f of x equals 2 to the x is the same as y equals 2 to the x. So if I want to find the equation of the inverse, what's the first step? Switch x and y. So x equals 2 to the y. So what's the next step? But we have to get the y alone here. And right now, this annoying base of 2 is on it. So how can I get rid of that base of 2? How to solve for y? Well, what I just said is true. We need to get rid of the base 2. Need to get rid of the base, which is 2. So how do we do that? Up to this point, we haven't had a function that gets rid of bases, but now we do. This new function is called a log. And even more than that, it's actually a log with a base b. So I call that little thing the base here. And it's written as a subscript, so if you were writing on a line here, you'd have log with a base of b kind of underneath it a little bit. And like I already told you, the inverse of exponential functions are logs. And the big idea is if the base of the log matches base of the exponent, they cancel out. The base of the log matches the base of the exponent, they cancel out. Okay, so that idea is similar to what you know about the different roots. Square root, third root, fourth root, fifth root. So I'm just going to say similar to roots, because that's kind of what you want to think back on. That's what you know already. If I had x cubed and I wanted to get rid of the cubed, what would you do? Well, you wouldn't take a square root, because a square root isn't the same as, that would get rid of a square, not a cube. You'd take a cube root. So kind of the root matches what's on the exponent here. And since that happens, they cancel each other out, just leaving us with x. Okay, well, the same idea would happen if I had 3 raised to the x power. Now I don't want to get rid of the exponent anymore, like this 3. I want to get rid of the 3 that's a base. So what gets rid of the base? Well, that's what we're talking about now. I would have to take the log of both sides. But it's not just a log, it's a log base 3. Again, similar to this idea of taking the cubed root to get rid of the 3 exponent. This log and the base of 3 cancel out, and I'm left with x. So in general, if I have log base b of b raised to the x power, that log base b and the base of the exponent b are going to cancel, leaving us with just x. Okay, so that's the whole theory. That's really the most important stuff of today, is understanding that right there. So if I go back over to here, now if I want to get rid of this 2, this base of 2, what do you think I need to do to both sides? I have to take the log base 2. So I'm doing log base 2 of x, and it's a good idea to put parentheses, equals log base 2 of 2 to the y. Okay, well, how does that help me? That gets this log and that 2 to cancel. So now I just have y over here. And this is going to give me log base 2 of x. And that's basically my answer. So conclusion down here, if f of x is equal to 2 to the x, the inverse, f inverse of x, is equal to log base 2 of x. And I know this might look a little weird right now, but again, it's really no different than taking roots to get rid of exponents. Now we're taking logs to get rid of bases. Okay, so once you got all that written down, hopefully I'm not going too fast for you. If not, you can always rewatch the video tonight because it's posted on my website online. How fun would that be? Relive class. Soup fun. Okay, come down here. Here's example 2. Solve for y in terms of x. So you want to get y alone, and your answer is going to have x in it. So to get y alone here, I got to get rid of this 4. What could I do to both sides? I would get rid of this base of 4. Hopefully you're all screaming, take log base 4. So log base 4 of x equals log base 4 of 4 to the y. Log base 4 and the 4 cancel. So I have log base 4 of x equals y. And now I've solved for y in terms of x. So to get y out of the exponent, you take the log of both sides. We're always going to use the same base to get rid of that exponent. Okay, so C. Well, let's go down to B. X equals 5 to the y. What would I do to both sides? Take log base 5. So log base 5 of x equals log base 5 of 5 to the y. The log base 5 and the 5 cancel, leaving me with log base 5 of x equals y. That's my answer. Over to C up here. X equals 0.25 to the y. Just take the log 0.25 of both sides. So log base 0.25 of x equals log base 0.25 of 0.25 to the y. These cancel. Log base 0.25 of x equals y. And last one, x equals 4/3 to the y. Going to take log base 4/3 of both sides. So log base 4/3 of x equals log base 4/3 of 4/3 to the y. Cancel it out. Log base 4/3 of x equals y. Soupies. All right, good. Hopefully that made sense. On to page 3. Okay, kind of like the first one now. Consider the exponential function f of x equals 1/3 to the x. Using your calculator, sketch a graph of f of x. Okay, so we're going to make a table of values again. Here's x, here's y. This is just a regular exponential, so -2, -1, 0, 1, and 2. And we could use our calculator if you really want to. Here's your calculator. Go over here, plug in 1/3 raised to the x. And you can look at your table. And there's our values. It's going to be 931, 0.3 repeat, 0.1 repeat. Okay, so you can just copy those over to your table if you want. Or you can be a smart math student and say 1/3 to the 0 is, well, anything to the 0 is 1. 1/3 to the first would be 1/3. That's the same as that 0.3 number you saw right here. And 1/3 squared, well, 1 squared is 1, 3 squared is 9, so that's 1/9. And that's the same as that 0.1 repeating number you saw there. Okay, and if 1/3 to the first is 1/3, what would 1/3 to the negative first be? Remember, negative just means flip it, so flip 1/3 and you get 3. And 1/3 squared is 1/9, so 1/3 to the -2, flip 1/9, you get 9. And now we can plot. So -2, 9. There. -1, 3. 0, 1. 1, 1/3, right about there. 2, 1/9, a little bit lower. There's your exponential decay function this time with regular asymptote of y equals 0. And make sure you label that. This is f of x. Here's our original function. All right. So horizontal asymptote, we know for exponentials, that's always y equals 0. Y-intercept, we know that always starts at 0, 1. Domain, this time they want set builder notation. Okay, so the domain and set builder notation would be all x such that, okay, well, domain, we know of exponential functions is always -infinity to infinity because it goes all the way left forever and all the way right forever. So in set builder notation, that looks like negative infinity less than x less than infinity. The range, we know it goes down to 0, but up to infinity. So we can just write that as all y's such that y's are greater than 0. Remember, not greater than or equal to 0, because 0 is an asymptote. As x goes to infinity, as x gets huge, what's happening to your y values? They're getting smaller, but not to negative infinity. They're only getting smaller to 0. And as your x values get small, what's happening to your y values on your graph? Those are going to infinity. All right, now I want to sketch the graph of the inverse. So how did I do that last time? Well, if you've got a table for your original, what do you need to do with that to get a table for the inverse? Just switch x and y. So 9, negative 2, 3, negative 1, 1, 0, 1/3, 1, 1/9, and 2. Okay, so go ahead and plot those up here. We've got 9, negative 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 2 is right about here. 3, negative 1. 1, 0. 1/3, 1 would be about there. 1/9, 2, maybe about there. So connect those points, see what you got to work with. And remember, like last time, you're going to have a vertical asymptote at x equals 0. Because that y equals 0 asymptote from before, when we switch x and y, it's going to turn into x equals 0. Again, make sure you label which graph is which. So that's f inverse of x. All right, let's go down and fill in the information about the red graph, f inverse of x now. Vertical asymptote, we just said that was x equals 0. X-intercept, since it always starts as a y-intercept of 0, 1, it always becomes an x-intercept for logs of 1, 0. Domain in set builder notation. Let's go back up and look at that graph. Farthest left it goes is 0. There's no red on this side. So the farthest left it goes is 0. Farthest right it goes is infinity. So in set builder notation, that would look like all x such that x is greater than 0. And for the range, what's the lowest that red graph goes? Scroll back up and look here. It's going down here. It's getting lower just slowly, so it does go to negative infinity eventually, and it gets up to positive infinity. So that would be all y such that negative infinity is less than y is less than infinity. Again, what happened? Look at those. Look at those. Ah, they switched. Why does that totally make sense? Because you switch x and y. That is so great. Okay, and then end behavior. As x goes to infinity, so my x values are getting huge. What's happening to my y values? They're getting smaller and smaller and smaller, and those do go down forever because there's no asymptote down here. So we'd say y goes to negative infinity. And as x goes to 0, what's happening to y? Well, here's my x values getting closer to 0. If I follow that along on my red graph, we're approaching positive infinity because y values are going up forever. So that's positive infinity. All right, and then finally, write the equation of the inverse function. Okay, when you see these, immediately change this to say y equals 1/3 to the x. Then do what? Flip x and y. X equals 1/3 to the y. Then what? We got to get rid of this 1/3 so we can get y alone. So what does that? Log base 1/3. So log base 1/3 of x equals log base 1/3 of 1/3 to the y. Cancel those out. We get log base 1/3 of x equals y. So our answer, f inverse of x, is equal to log base 1/3 of x. Any questions? Hopefully not, because I don't know what you're asking and I can't answer you. But hopefully that makes sense. All right, last one. Over to number 4. Ready to go on? Here we go. Consider the exponential function f of x equals 3/2 to the x. Okay, let's make a graph of this. We could use our calculator. Let's try to be smart and do it without. We've got -2, -1, 0, 1, 2. Let's start at x equals 0, because we know 3/2 to the 0 is going to be 1. How about 3/2 to the first? That would just be 3/2. What about 3/2 squared? Well, square the top, we get 9. Square the bottom, we get 4. So this is 9/4. So if 3/2 to the first is 3/2, what's 3/2 to the negative first? Negative just means flip it, so 2/3. 3/2 squared is 9/4, so 3/2 to the negative second is 4/9. And again, your calculator would tell you the same thing, just with decimals. So let's plot it. -2, 4/9. It's pretty small. Be right about there. And then -1, 2/3, a little bit bigger right there. 0, 1. 1 3/2. 3/2 is 1.5, so right about there. 2 9/4. Well, I know 9/4 is just a little bit more than 2, because 8/4 would be 2. So probably right about there. And then connect your points, and there you go. So this is f of x. And don't forget to draw in your asymptote at y equals 0. All right, inverse now. I'm going to sketch a graph of the inverse. We need a table. How am I going to get my table? Switch x and y. So 4/9, -2, 2/3, -1, 1, 0, 3/2, 1, 9/4, 2. Go ahead and plot those. So 4/9, -2 would be right about here. 2/3, -1, right about there. 1, 0. 3/2, remember, is 1.5. 1 would be right about there. Then 9/4, which is a little bit more than 2, and 2 would be right about there. Connect those, and there's your graph. This is f inverse of x, and it would have a vertical asymptote at x equals 0. All right, and last thing, write the equation of the inverse of f of x equals 3/2 to the x. Here we go. First step, y equals 3/2 to the x. Second step, switch x and y. X equals 3/2 to the y. Third step, take log base 3/2 of both sides. Log base 3/2 of x equals log base 3/2 to the y. That gets that 3/2 base to cancel out. We've got log base 3/2 of x equals y. So our final answer is f inverse of x equals log base 3/2 of x. All right, that is it. Hopefully that made sense to you. If not, like I said, try to rewatch some of the videos tonight. It'll be posted on my website. You should be able to watch it on a phone or your computer. And homework tonight is a worksheet. So make sure you get the worksheet before you leave today.